Welcome to our lecture on dashboards to statistical inference. We're drawing a lot of this material from chapters 5 and 6 from the Pease, Bierley, and Fitzen's book, but we're also going to include some other material related to some of my other research. What do dashboards tell us? Dashboards are data reports that frequently supply descriptive statistics, basic checks on the health of your business processes, and in this case we're talking about human capital processes, interim findings to stakeholders in advance of more robust research programs, built-in culture of empirical evidence rather than impressions, so that by using dashboards we can get people more focused on metrics and facts rather than their impressions about what's going on. And since a lot of stakeholders won't understand or trust more advanced analyses, they don't have the background to really grasp what a multiple regression tells us, for instance, we want to help them to start to build an understanding of what metrics are and how to use them. Dashboards can also be updated on a real-time basis depending on the systems we have to support them, and it gives us a chance to create a more fact-based environment and to challenge some of the basic assumptions that people use when they're doing their work. The idea of a dashboard is to provide an at-a-glance view of the KPIs. It's a metaphor for the car or the airplane meters that you see today, although in modern times there are fewer meters and more what you might call idiot lights, like this little light that goes off to tell you when your oil is low. Unfortunately, the little light only goes on when you're down to 1/4 of oil and your engine is just about ready to explode. So hopefully the dashboards we create will give us more advanced warning and give us a clearer understanding of how to repair damage before it gets too bad. Dashboards provide an early warning alert, and again, depending on how early the warning is given, is how we build these metrics, what KPIs we use. So we want to use more lead metrics that are consequential for the future. And typically they highlight data, summaries, key trends, comparisons, and exceptions. Here's an example of a dashboard that I took off the internet. You'll see that there's a mix here of different metrics, and these are metrics related to an hypothetical internet site, and we look at the views over a given period of time. We could see visits to the website, page views, visits per page, new visits, bounce rate, and the average site time. We have a display in terms of referring site, direct traffic, and search engines used, and this is a little pie chart here that gives us both the number and the percent. And then we have bar charts that give us the usage over time in a time series. And then as we look in our goals section, viewed 3+ pages, viewed 3+ unique pages, etc., it gives us a readout on each of those KPIs. So this is an interesting view of the website, and it highlights the key summary here, and then we get the details here. A dashboard can be in multiple pages, and so our data can be broken down as it is in the menu, and so we have more pages to view than the one that's displayed here. Here's one related specifically to human resources, and again you'll see a variety of KPIs. Staff turnover in the upper left-hand corner, a comparison year over year, so we can look at a 10-year average of turnover. So this historical data is useful for comparisons, but should give us the most recent data. We look at the payroll structure by the top 5 employees. We have the payroll structure summary here. We have staff turnover by department. We have absence duration for the top 5 employees. And we have absence reasons, whether it's sick leave or, vacation. So it's cut off at the bottom a little here, but each of these bars is a specific employee. Now, whether or not this type of display makes sense, this is just a hypothetical. I'm not saying that this is the best kind of HR dashboard, but it just illustrates the point of the kinds of visuals and the kinds of KPIs that could be handled in an HR-related dashboard. Here's another set of displays, and you could go online and you could see all sorts of graphics to stimulate ideas. This is related to sales, so this is more of a business and revenue type of dashboard, not specific to HR, but it also gives you some idea as to different kinds of visual displays. Now, our textbook talks about the different types of dashboard data that we might include. It emphasizes a time series type of bar chart that gives us a basic overview, and all the illustrations in the text are basically simple. Jack Fitzens, who I have talked about in the past, who started the Saratoga Institute for HR Benchmarking, has always been interested in simplicity, and the simplicity is, as I said in the opening slide, as much to do with what people are ready to understand among the stakeholders, and we have to try to keep things simple until the organization culture is ready to handle better information. Here we have a comparison. It's another time series, but in this case we're using line charts, and we're doing a 2-year comparison here, so we can see the different trends year over year. We can make quick visual comparisons, and making the axes clear in terms of what's being covered in each axis is key to one of these displays. And what we're seeing here is the connectedness from month to month, the trend. So lines are really good at dealing with the visual display of trends. When the book talks about descriptive steroids, statistics on steroids, we're looking at combining data from different sources. And that combination is going to leave an impression and have some educational value. The intersection of the data from many sources offers insight, and that's what we want to build here. We're not just looking at reporting for the sake of reporting. We're trying to create and build insight, and that depends on the understanding of the audience. It also depends on how the particular dynamics of the organization lend themselves to different kinds of interpretation. So we have to do things, use our descriptive statistics in the context of the industry we're in, the type of organization, the culture of the organization, and the common level of understanding of what each of these metrics mean. Our textbook looks at a series of HR-related metrics. These are simple bar charts, and as you can see the story, we have turnover rate by department in percentage, And obviously you can see that manufacturing has the highest turnover rate. And if we look at 5.4 absenteeism, manufacturing also has the highest rate of absenteeism. And then when we go down to training, we also see that there seems to be a negative correlation between training rate, turnover, and absenteeism. So the highest engineering is the highest training rate. It's also the lowest turnover rate and the lowest absenteeism rate. Now, is that a causal relationship, that the training is actually causing that? We don't know. I'm going to have to investigate. But now when we get to the fourth one, and we see a comparison of, and I apologize because the screen blocks out the labels, but the diamonds here are, this line represents retention rate, this line represents training rate, and we see a very strong correlation between the two. Now, what does that correlation mean? We're not sure. We're going to have to investigate that further. Okay, so the view here tells us that it's time to take a closer look. It doesn't specify what the message is here, but we know we have to go forth and do some more research. So now that we've understood that we need to do some more research, let's take a look at one of our key research tools, regression analysis. And I'll go into this in a little bit of depth. I wish we had more time to go over statistical tools, but we'll try to at least introduce some of these tools conceptually. I'll go into more detail next class on others. So what's correlation? A correlation is a single number from +1 to -1 that describes the degree of relationship between two variables. Our correlation material is drawn from this website, which I found to be a pretty good kind of online textbook for basic concepts, the socialresearchmethods.net. So feel free to go in there and do some more studying to help you understand statistics. What correlation does not imply is what? Correlation doesn't imply causation, and you'll hear that over and over again. And if you look at any textbook on correlation, you'll see that just because you have a high correlation, close to 1.0, positive or negative, it doesn't necessarily mean that one of the variables is causing the other. So here's some examples given in the textbook, that the weight of elementary school children is highly correlated with their math scores, but is there a causative relation there? Well, to a certain extent there is, because the taller you are, the older probably you are, and therefore you're more advanced in your math aptitude as you get older because you've learned more math. But there are some intervening variables there which don't have anything to do with height, except that height is correlated with age, and the longer you're studying, the more likely you're going to learn math. So these are other examples. I like the one on the stock market. Everybody is trying to figure out what are the correlates to the rises and falls in the stock market. I've had some very brilliant professors who wish they could use their knowledge of statistics to beat the market, but the market behavior is complex, kind of like the weather, and so it's very hard to predict. I'll give you an example. What is the relationship between height in inches and self-esteem? Our hypothesis would be that your height affects your self-esteem. And this has been actually studied to some degree in the literature, and I'm not going into the real research literature on it. I just want to give an example here. but it's believed that people who are taller throughout their childhood and throughout their early adult years tend to have a better self-concept and perhaps might make, let's say, better salesmen or better leaders. Assume that we don't really know the direction of the causality here. It's not likely that self-esteem causes your height, right? Because height is an inherent trait that comes to you biologically. So if there is a relationship, we have to assume that the relationship is going in that particular direction, but we're not going to assume that we know that direction. We collect data for 20 individuals, and we're keeping them all male because we don't want to contaminate the results with the complexity of gender, which has some relationship to height, and it may have some other relationship to self-esteem. So height is measured in inches, and self-esteem is based on a 10-item, 5-point scale measurement. So here's the data. We have 20 men, we have their heights reported, and we have a self-esteem rating that's an average of those 10 items. So we can lay that out. The height is laid out on a bar chart, and here we have the number of people who are at various levels of height on 2-inch intervals. I apologize, my thumb screw here is about ahead of me. And then we have self-esteem, the number of people who score at different levels of self-esteem. And here we see that it's not quite a normal distribution, but we're only looking at a small number of people. We only have 20 people. If we had maybe 2,000 people in our study, maybe it would be more normally distributed. And here are some of the basic statistics related to the variables. We have a mean score, which is the mathematical average for height, which is the mean height is 65.4 inches. Again, this is made up data, so it doesn't represent any real population. And the mean self-esteem score is roughly 3.8. And we have the standard deviation, the variance, and you'll see that the standard deviation is the square root of the variance by definition. We have the sum, the total of the 20 people on their data for height and for self-esteem. And then we have minimum values, the lowest height value, and we have a range of 17. And the self-esteem scores, we also have a range of 1.5 from 3.1, the lowest, to 4.6. Now, if we were to lay these 20 data points on a scatter plot, this is what it would look like. And you could start to see that if we were to think of this in a linear way, we would probably see some kind of a line that looks like this. Man, that's a pretty good line. And we have some outliers. We have an outlier here that doesn't seem to fit with the rest of the pack. This is a little bit of an outlier here. But basically what we see is just visually there's a strong relationship between height going on this axis and self-esteem going on this axis. And so visually, and this is very important, visually we should be able to look at the data and get a sense of what the relationship is, and also if there are any anomalies or a lot of outliers, or another condition called heteroscedasticity. Heteroscedasticity is when, as you move through values on one dimension, we start to see a uneven distribution. So we would have a heteroscedastic condition if, let's say, everything was tightly packed down here and kind of linear, And then as we go further out in the height distribution, we have more variability. That would be heteroscedasticity. This, on the other hand, is a fairly tight distribution visually. We would call this a kind of a homoscedastic distribution. Now here's the formula. R, which is the correlation, and we have the number of pairs, and we have the sum of x values, which would be height, and y values, which would be self-esteem. We would multiply them, and then we would subtract from that the sum of the x's multiplied by the sum of the y's. That would be our the top of our calculation here. And at the bottom would be the square root of these values that we create by the sum of squares of x times the number of people. Then we take the sum of x squared, and then that would get multiplied by the number of y values, the sum of y squared, and the sum of y's squared. So n is the number of pairs of scores. Sigma xy is the sum of products of paired scores. Sigma x, the sum of scores, etc. So here's our definitions. And you can actually calculate this by hand if you wanted to, or you could do this on Excel, and I'll show you. You don't need a fancy statistical tool to do a correlation. And so here's the data calculations, and the 20 people are listed. We have their height, x values, their self-esteem, y values, and we have their products in multiplication. We get the values, and at the bottom of this display, which you can't see, which is below the video, is the actual summary data that is listed up here. So at the bottom of those columns are these data. Okay. Now, as we go through the calculations, if you wanted to do it just to check it out, you would see that the resulting value for R is 0.73. That is our correlation. The R squared, which would be the explained variance between one and the other, would be roughly around 0.49 or 0.5, which is a moderately high. Almost half of the explained variance in one variable is explained by the other variable. So if we know one, we know half of what's going on in the variability between one and the other, and that's a pretty high value. If we only know one of these variables, we know a lot about the other variable according to this formula. And again, we have a sample of 20. So one of the questions we might ask is this value 0.73 by chance, or is it really the right correlation? If we were to take hundreds of samples of 20 people, would we come up with similar results? Well, the way to answer that would be through a significance test, and the null hypothesis, which is R equals 0. There is no correlation, and this was just a fluke. This was just an accidental correlation by chance because of the 20 people we took. And the alternative hypothesis is that it's a real correlation that didn't occur by chance. Here's another display, and I created with my co-author Anton Armbruster, we created a leadership development profile, which is basically 135 item questionnaire. It takes about 20 minutes to take. And it gives us scores on 9 different dimensions, which are labeled here. So principle-centered is one of the factors. Relationship-focused is another factor. These are kinds of traits of the individual person that we're measuring. And then I'm using a spider diagram to illustrate a particular person's scores. This is Susan Anonymous, one of my former students. And these are her scores on this particular profile. We're not talking about the profile in depth for the purpose of our class. At some point before the end of the semester, I may get into it more if you're interested, but this is basically a personality type test that creates 7 different types. And if you are a certain type, we believe that there is some correlation to certain work-related behaviors, specifically leadership types of competencies. So up here is an analysis that takes these 9 scores and then breaks them down into 3s. And so we have an aggressive score, a compliance score, and a withdrawal score. And these are based on the work of Karen Horney, the famous social psychologist, and we call it an Hornevian analysis of the same data. So we can tell the balance in the person's personality, whether they're more likely to be aggressive in acting out, whether they're more likely to be compliant and accepting and supportive of whatever the leader wants to do, or whether they want to be withdrawn and tend to work by themselves and not necessarily engage with the rest of the team. So this is a breakout of an individual profile for that. If we were to take these 9 traits on the LDP and we would create a correlational layout here so that we correlate each subscale of the LDP 2.2 against the other subscales, we see that when we compare each scale to itself, we create a correlation of each scale to itself. We get a 1.0, and that should be obvious. And now we see the correlations. We see the correlations between one LDP factor and the other 8. And so here we have here we have the very low correlation, which is close to 0. And then we have some very strong correlations like this 0.53 between performance-driven and adventure-seeking. So performance-driven is a high achievement-oriented type of profile. Adventure-seeking is a person who loves new experiences and really enjoys their work. So this kind of correlation is not totally surprising, but we would have to investigate further. This is based, incidentally, on a sample of about 300 people who took the test. So the n equals 300. And when we look up at a probability table for Pearson correlations, and you can get these kinds of tables in any stat book or online, you can just Google them and get all these types of tables for probability. We would see that at the 1.9 level of 0.01 level of probability, a correlation as low as 0.113 would be statistically significant. And so, I'm sorry, I misread that. At the 0.05 level, it would be 0.113. At the 0.01 level, it would be basically 0.149 or 1.5 for a group of 300 people. So almost all of these correlations are statistically significant, and we're choosing a two-tailed test because we don't really know if there's a directional relationship in correlation between one variable and another. So basically, here's our table. The correlations, and again, this is a fairly robust sample of 300. However, although we believe these correlations are pretty real, we don't know if in fact in a large population of people whether or not these are exactly the correlations that we would come up with. But we would have to investigate why there is such a high relationship between some of these traits and why there was almost no relationship, like in the case of principle-centered versus alliance-seeking. Now, a principle-centered person is somebody who, by definition, likes to play by the rules, has a very strong sense of ethics and responsibility, whereas an alliance-seeking person is one who likes to work in concert with others, somebody who doesn't necessarily care about ideology, but is more importantly interested in making peace and having people work together. So alliance-seeking people tend to be pragmatic. Principle-seeking people tend to be more ideological, and therefore we see there's almost an orthogonal and non-correlated relationship between the two, and that kind of makes sense. Now when we get to the highest correlation on the table, which is 0.60, that's moderately high by any standard. And we have the adventure-seeking person, who's a really fun-loving, experience seeker, who likes to do new things, who gets bored easily if we're doing the same thing over and over again. Oh, here we go again. And a results-driven person who's kind of a typical CEO type, who wants other people to do things his or her way, who's very power-oriented. There seems to be a high correlation between these two. Now, we would have to do more statistical analysis to see if that correlation is because maybe the order of the variables, that the questions for adventure seeking are closer to the results-driven questions than the other item sets. We'd have to take a look at this both theoretically and through item analysis to see if this is a real correlation or if this is caused by some artifact. The real correlation we would refer to as true variance, meaning that there's a meaningful phenomenological relationship in reality, and then everything else is called error variance, variance that's introduced into the situation, the relationship, because of some form of accident or circumstance. I also wanted to get into this issue of reliability, and this particular website that I have listed above goes into some great depth as to what reliability is, and it's talking about the quality of the measurement. In its everyday sense, reliability is the consistency or the repeatability of the results that you get on a particular measure. And in order to have validity, you must have reliability. So if a measurement is going to be valid, it also must first be reliable, because if you have a measure that has a lot of error variance in it, where different people will interpret the measure differently when they're scoring it, when people taking the same test over time don't come up with the same types of results, it's not very stable over time, then it's hard to have validity. And we'll get more into validity in our next lecture. Some of the research that I've done on measurement, we look at the variable itself, we look at the attributes of a variable, we look at the values, that are assigned a variable, and we can test the relationship of the variables. So these are ways of talking about measures. So an example of variable might be if you were doing a poll and you ask people what their party affiliation is. So the party affiliation would be the variable, and the three buckets or three categories you offer them in the answer set would be Republican, Independent, or Democrat. And we would assign those a value on the survey of 1, 2, or 3. Then that would generate data, and we would be able to create the correlation. There are basically 4 different levels of measurement called nominal measurement, ordinal measurement, interval, and ratio. Nominal measurement is basically no numerical value, it's just a name. So as we saw in the previous variable, we're talking about Republicans, Democrats, and Independents. That's a nominal level. It doesn't imply anything in terms of value, just identifying people by name. Ordinal would be the attribute can produce a rank order. So we don't know if the difference in rank between the first and the second is necessarily the same distance as between the third and the fourth, but we know one is higher than the other. So if we were to rank employees in terms of their productivity, saying that she's the first in the rankings doesn't tell us how much more she might produce than number 2 or the guy who's number 3, whatever. We get that distance in an interval type of measurement, and the distance between intervals is meaningful. So if we were looking at the temperature scale Fahrenheit, we would see that the distance between 30 and 40 degrees is exactly the same in physical measurement as between 70 and 80 degrees, and so there's meaning about that interval. And by far the most complex and useful type of data is ratio data, and ratio data has an absolute 0. So if we were talking about weight of an object, that would be ratio data, and we can make comparisons based on the understanding that there is such a thing as an absolute 0. So that's basically the first unit I wanted to talk about in terms of statistics. If you were to go into Excel, you could actually see how to calculate what you might want to do. If you want to try this on Excel, the command is CORR, oops, let me get rid of this. The command is CORREL if you want to do correlation of the 2 columns. You might want to test it out on the test data that I gave you. Please email me if you have any questions, or we can talk about it during next class. Take care. Have a great Thanksgiving.